이번에 그 마지막 발표로 현재 햇폴드 컨설팅 인터내셔널에 재직하고 계시는 마이클 더프 책임과 뱅거트 선생님 모시고 순차적으로 그 dynamically model the impact of decision on energy consumption and affordability parameter에 대한 발표를 드리겠습니다. 뜨거운 박수로 마이클 더프 책임과 뱅거트 선생님을 모시고
Good afternoon. I'm glad that we can satisfy the previous speaker's desire for some foreign speakers on the stage. My colleague Bengt and I work in a private practice in London called Happold Consulting. We are strategic planners, urban designers, and we work on the development of eco-cities in various continents in the world. In particular, right now we're working in the United States and in the Middle East on eco-city concepts. I'd like to thank the hosts of today's event, and in particular Dr. Woo-Young Kim, who invited us here today from Harvard University. Happold Consulting, our practice, is a founding member of the Harvard University Working Group for Sustainable Cities, of which Dr. Woo-Young Kim is also a member. Today I will be presenting the research side of some research work that we undertook, supported by the University of East London School of Architecture and Visual Arts, and University College London's Bartlett School of Graduate Studies. And then I'll pass the presentation over to my colleague Bengt, who will take you through some specific examples of how we used some of this research in our private practice developing eco-cities. So, the U-city is often misinterpreted. One of the presenters yesterday put up a cartoon face showing the surprise that some people express when the U-city concept is described to them. Often the kinds of images that you see on screen now, very futurist, very cartoon-like images are used to describe this. But today I'd like to take you through a designer's perspective of the U-city. First of all, the U-city is dynamic. The concept of the U-city will have unlimited users attached to it. These users are ever-changing, their behavior alters daily, their number is unlimited, and the concept is for a vibrant and lively economy and community. The U-city is decentralized. So a concept such as U-city allows us to move away from centralized traditional models of city planning, where everything happens from the center out. Location becomes less important. Information now comes straight to the person rather than being location dependent. The U-city could be described as recursive. So the idea of recursion is that the processes are continually running. The analysis is happening constantly. So a U-city system is able to analyze information as it comes in, learn about itself, and adapt itself to changing behaviors and changing demand. The U-city, as we've seen in all these presentations, is data rich. There's ubiquitous technology, but in fact there's actually ubiquitous information. There are many, many connected devices, sensors, mobile phones, PDAs, buses, individuals, and all of these devices are providing information. The U-city is responsive, so it responds to demands in real time at real locations. The U-city is parametric. So essentially the behavior of objects within the U-city, the responses that various systems give to demands from people are governed by a set of rules, a set of pre-programmed responses, and as time goes by, these responses get more and more accurate. The U-city is alive. Now this happens in two ways. The U-city is alive in that it responds instantly to demands, but I think more interestingly and more importantly, the U-city is alive as an evolving idea over the coming decades. We look outside now at SongDo U-city, and actually it is a city that looks fairly similar to other cities. But imagine if SongDo is happening now, what does a U-city look like 50 years from now? So this concept is something that's going to grow and change over time. And at present, we probably can't predict what a U-city looks like in 50 years. A U-city is resilient. So by resilient, I mean it's a durable, distributed structure. So thanks to being decentralized, both physically and in terms of its information, the uCity, should it have any problems, should it lose certain users, is a structure that will continue functioning. Finally, the uCity is adaptable. Obviously, as it proceeds through using the information in the analysis systems, it can learn. Its responses can become more tailored. It can become user appropriate as the city database gathers more information and the control center is able to respond. And what Bengt and I will argue today is that if that city database, if all of that data that's gathered is fed into the design process and given to the hands, through city authorities, given into the hands of designers and urban designers, landscape designers and architects, the uCities that are built in the future will become even more appropriate, even more specific, even more desirable, and even more have even more quality of life for their inhabitants. So this is the summary of the concepts I've used to describe the uCity. Now I'd like you to keep those in mind while we do a little thought experiment. I'd like to think a bit about what sustainable design is. So typically, sustainable design can be described with this tripartite division, that in fact all things that have to do with sustainability in cities are either environmental, social, or economic. But sustainability really is more importantly about the intersections of these zones. So in fact, that a lot of the elements and the elements of cities are in fact both environmental and social, or environmental, social, and economic. So really it's this space of the diagram that actually becomes more important when we're talking about what sustainability is. It's integrated design. So in fact, is this a better diagram? Do we need the three circles? What we're actually saying is that all of the elements of urban design, all of the elements of city design and sustainable design are at once environmental, social, and economic. And we need to think of them in through these three lenses. So quite an interesting way of showing this is what looks like a computer code networked model. Imagine all of these dots on screen as the elements of sustainable design, the elements of urban design, the elements of a uCity. What this diagram illustrates is that, in fact, rather than each element being just environmental, just social, or just economic, they're all connected to each other. So any action taken on one of these dots within the urban system will have consequences on all the other dots within the urban system. So if our cities are complex and non-linear and interconnected, what my colleague and I would like to argue today is that our design should be complex and non-linear. Current city design, however, if we look at examples from around the globe, isn't really complex for the most part and is fairly linear. In fact, I would describe it as static, centralized, linear, closed to new data, inflexible, frankly boring if you look at the image in front of you, and uncompliant. So what I'm actually saying is that I think sustainable design is all of the same descriptors that I use to describe the uCity. Dynamic, decentralized, recursive, data-rich, responsive, parametric, alive, resilient, and adaptable. So what we're saying here, historically speaking, designers have used technology to do things that humans could already do, but slightly faster. So we've used AutoCAD to draw, because it's better than drawing with a pencil. We've used a computer to calculate because it's easier than counting on our fingers. The other spectrum that we've used technology for is to generate incredible forms, thinking of buildings like the Guggenheim Museum in Bilbao. What we're actually proposing isn't very simple use of computers and isn't very complex use of computers. We're talking about something in the middle. We're not suggesting that we try to model every single parameter inside a city. This would be both impossible and unnecessary. None of us in this room would be alive long enough to understand all of the systems that make up an urban conglomeration in order to work out how to model all of these things. So we don't need to model all of those. What we're saying is that small computation can actually add significant value to the design process. So the purple lines that I've highlighted in the diagram on the screen suggest modeling a few relationships. For example, in an eco-city concept in the Middle East, we would suggest using small computation to model the most important concept. In the Middle East, it would be water, most likely, perhaps taking advantage of solar energy, and in the case of some of our projects, affordability, as affordable housing is a rarity in the Middle East at present. So really, it's a hybrid of human reasoning and computational modeling. We're not suggesting that the computers do everything, but we're suggesting a move away from the traditional design, which depended on the artistic brain of a specific architect to sketch a beautiful plan for a city. I'd like to hand over to my colleague Bengt now to present.
Very quickly, I'm going to try and introduce you to some different computational methods. I'm conscious you're all probably quite hungry. And then some examples of city-scale applications from our work at Apple Consulting. Both of these structures behind me look digital. We're more familiar with computational methods applied to single buildings than to cities. The port terminal on the left is produced from many complex drawings, but the complex roof on the right is produced algorithmically from 300 lines of code. And this is an important distinction. This algorithmic thinking, when applied intelligently, the same algorithmic thinking that produced the roof over the Great Court of the British Museum, could be a very efficient way of resolving complexity, but is actually less flexible than traditional CAD, which replicates drawing by hand and all the associated freedoms. Importantly, however, the inputs are variable within the constraints of the model. This project too demonstrates the complex relationships, outputs, and inputs the designer must define. The adaptable module on the right and at the bottom right can be very efficiently assembled to produce many different towers, but any change to the geometry of the module and the graph on the left must be completely rebuilt and all the relationships re-established. The designer is firmly in control and should remain in control, but computers are better at lots of very simple calculations. We advocate that computers should challenge preconceptions, not generate final city plans. But there is a well-founded fear of computer methods and generating designs from overly simple rules. And I think this is partly to do with the accountability. When designing a single structure, it is very clear that the chartered engineer is responsible and who to prosecute if something goes wrong. Who is responsible if we design a bad city? And indeed, how do we judge a bad city? It's very subjective. When designing single structures, we have a large amount of empirical data backed up by centuries of Newtonian mechanics. But our cities are manageable in their cognitive complexity. And then too, the testability. Do we build prototype cities? We're comfortable building prototype buildings and then scaling them. And I think that currently the design process outputs do not document design thinking well. They're very difficult to interact with and cannot be adapted. I think this is probably due to tensions between the designer or designers, the client, and the anticipated population that will inhabit the final design. I think that this output and the fact that it is not a very robust output is actually why a number of designs are never even implemented. And we think there might actually be a third way, and we've called this object-oriented planning, which is a programming analogy. And it's a technique that harnesses expert knowledge but also leaves room for wider participation, as well as the uncertainty that arises when you're dealing with a complex urban system. It is the combination of interactive models that enable real-time visualization of changing variables that require no prior knowledge of CAD. These are very important, and the ability to interact with them is very important in building trust in the design, building the capability of the client, and allowing variables to be redefined when new information becomes available. This is something we have found particularly a problem in the Middle East, is accessing data. It is also very important to be clear that you know what you do not know, be transparent, and not pretend that the constraints ensure the model is only capable of producing good designs. It is important to remember that it is impossible to completely mitigate against the risk of black swans. That is to say, unpredictable, high-impact events. So moving on to some example problems and possible solutions. Even simple search methods, computational search methods, for simple building forms can importantly challenge designers' preconceptions. This example shown combines three typically distinct sustainability parameters. Building 4, where energy efficiency and affordability meet. And this here shows the process of building this quite complex model. Firstly, in a traditional two-dimensional way, which is often how many problems are dangerously reduced. But as you can see, the complexity is then built up, slowly, dimension by dimension, because very few problems in reality are a simple XY graph with two variables. And there are certain things that you can plan for, but there are certain things that you simply cannot, things that are unexpected, combinations of events, and you don't know when they're going to happen, and you don't even know yet what they are. And so, when you deploy these tools, you have a moral imperative to do it in a way that they are adaptable. And this is an important distinction with traditional CAD that makes a profit from selling the product in a way that cannot really be augmented or changed or adapted. And here, this is the client interface for a project that we developed in Jeddah for affordable housing, which enabled the client to test different land use designs for a number of different sites in and around Jeddah. This additional piece of software extended that interface and allowed a 2D land use sketch, a design, to be imported and then its viability tested against the model developed by our engineers. It required no prior knowledge of CAD, and the input design can actually be re-evaluated and redrawn within this very simple software that was developed very quickly with the client so that the client understood how it worked and trusted it. And these are just some different input sketches. These could be actually overlaid in GIS and R for the real thing, but they just show how this can be turned into a 3D model, which is a 3D representation of the development, which also tests its viability. And this is another example of some work that Mike undertook at the University of East London, which imposed a grid onto a site and then based upon site considerations and the relationships between cells and their adjacent cells, started to generate plans which just began to challenge different preconceptions that designers might have when approaching the project. Here you can see a final render of what that looked like. And so what we're starting to find is that actually the way we develop these models, the thinking that underpins them, has actually started to influence planning policy itself, and our clients are starting to become interested in how algorithmic thinking can actually change planning policy, and planning policy can be more adaptable, more robust, and more resilient. And this is not really a new idea. We're familiar with Manhattan and how a small preserved church can sell the vertical space above it to an adjacent plot so that a large skyscraper can be built by a developer there, and also the associated zoning laws. And so, in conclusion, we say that the complexity of cities requires tools which tend towards the complex. We needn't be limited in our design choices by what has worked for us previously. The complexity of sustainability in cities makes computational city design an obvious choice. Computational modelling needn't be onerous, time-consuming, expensive, or impenetrable. Massive U-City datasets and computational design can advance sustainable design significantly. The U-City of today might look a lot like cities that we're familiar with, but actually provide us with a way of analysing the way we inhabit cities unlike any other. But it could also, in the future, be something much more complex, which will require more complex planning policies, and more complex tools to help us understand and design these cities. Thank you.
네, 감사합니다. 혹시 질문 있으신 분 계신가요? 예, 감사합니다. 이 시간이 너무 많이 지체가 돼가지고. 자, 공지사항 한 2가지만 먼저 말씀드릴게요. 지금 우리가 배포해드린 브로셔에 보면 공개 토론회라는 게 있습니다. 이 공개 토론회는 지금 세미나 일정하고 별도로 진행이 되니까 관심 있으신 분들은 지금 공개 토론회 같은